can slowly start welcoming everybody to what is already the last talk in our colloquium mini-series this summer. Thanks again for joining us. Up to this point, we've enjoyed some very nice theoretical talks on the general theme of thermalization and equilibration dynamics. And so it may be fitting and pleasant to be closing with an experimental talk. So I'm very happy to introduce Julian Léonard as our speaker. Julian got his PhD just a relatively short while ago in 2017 at ETH in Zurich, working with Tilman Esslinger. And since 2017, he has been a postdoc in Marcus Greiner's group at Harvard. In his young career, he has already done quite some groundbreaking work, studying fundamental questions about correlated matter in cold atomic gases, in optical cavities and optical lattices. This includes in particular the realization of a supersolid state of matter. His interests, moreover, range from correlation physics very far from equilibrium to topological states of matter to many-body localization. He's an expert on quantum gas microscopy. So indeed, we are very fortunate to have him virtually with us today and tell us about many-body localization under the microscope.
Yeah, thank you so much. I have to say I feel really honored to speak in this fantastic lineup over the past weeks. These talks are really great. And I'm really excited to give you a bit of as you mentioned, a bit of an experimental perspective at the end of this really nice series. What we studied over the last few years are systems that are non-equilibrium states of matter, and in particular, many-body localization is the main target of what we have been looking at over the past years. And therefore, I think it's nice to go back a little bit at what it actually means when we have a ground state or like a quantum phase that happens in the ground state, how we usually think about these kind of quantum phases. What we usually have in mind is some kind of order, and I've depicted here some very simplified kind of order, kind of checkerboard order where particles or spins are arranged in a regular fashion. And as we now look at quantum fluctuations around this very regular order, so we want to capture maybe some entanglement in that system, usually what we expect are some kind of fluctuations around this order. So that could, for example, mean that on one particular snapshot that we would take of this quantum state, these atoms are now slightly arranged around this order. So they are kind of, there's some uncertainty about this order on a local level, but on a broader scale, the order is still intact. That means in each snapshot, I would find this order. Now, in general, that's not always true. I may be, for example, measuring in a basis that is exactly orthogonal to this order, but overall, that's kind of the picture in which we usually think of that. And the reason why I want to mention that first is because, so yeah, on another snapshot, it may look different. So that's really the essence of this entanglement that we each time have a different many-body projection of the system, but with a slightly different microscopic picture. The reason why I'm mentioning this is because things can get really different when we now go far away from this picture. So for example, we would quench the system very strongly, we would inject a lot of energy into the system, and then this order is expected to disappear. And such a system that now has is at very high energies would not show any kind of order. So on one snapshot, I may see something like that. And if I take another snapshot of the very same quantum state, I may see something like that. So I don't expect any kind of order. And that's very much also in the spirit of what we heard over the past weeks, very prominently last week. When I thermalize a system, then any kind of correlations would get lost during this thermalization. Now, I want to talk about a system that does not behave like that. A system that has a lot of entanglement in it, but each time I take a snapshot of the system, it looks completely different. And I don't find any kind of correlations in the system whatsoever. So that means it is a quantum state, but just from snapshots, it's very difficult to find the entanglement in an individual shot from that. So there's no kind of perturbation of order in that system. It's something much more dramatic. I have to now take into account all of those different snapshots together, the knowledge of all those different projections of the quantum state, and only if I have the combined knowledge of all those quantum states, of all those snapshots, some order emerges. So it's not order within a certain snapshot of the quantum state, within a certain projection. It is something that I need to figure out through correlations over many different snapshots. And this is really one of the defining characteristics of many-body localization, and that's why it stands apart from that's one way how it stands apart from other non-equilibrium systems. So for many-body localization, we need 3 different ingredients. The first thing is, so we have a lattice model, and we can think of individual particles that now hop from one lattice side to another one. And if we do this in a quantum state and we just quench the system, that means we very rapidly let the system evolve, then we expect quantum walks in that system. Now, as we, on top of that, also add disorder to the system, those quantum walks become suppressed, and instead we expect particles to become exponentially localized around their initial position, what we know as Anderson localization. If we now want to study many-body localization, we need a third ingredient, and that is disorder. So we need now many different particles that interact, typically repulsively, and it turns out that despite those interactions, particles can remain localized under certain conditions. Many-body localization has a lot of different facets, and what I've mentioned so far are just a few properties that are so exciting about the system. One of those is, as I mentioned, that we have actually a localization in the system despite interactions. So repulsive interactions between particles typically tend to delocalize the system, but in this particular system, these tendencies are overcome, and particles can remain localized indefinitely. A second property, maybe more of a condensed matter or solid state type of property or picture, is that the system now is actually an insulator. It's a very good insulator, and despite injecting a lot of energy into the system. So this T here, this temperature, is with a grain of salt. It's not technically thermalized, but it is. I just want to visualize here that we have a lot of energy in the system, and yet we have a perfect insulator, which is something that we usually don't expect in systems. Another property is that the system actually memorizes its initial state. So the way I initialize the system, even after long evolutions, under these very high energies, the system retains some memory of those initial conditions, and that's what makes it very interesting candidate for quantum memories. From a very fundamental perspective, many-body localization is the only known robust exception to thermalization. So everything we learned last week is actually not true for many-body localization. So that's a very prominent exception to this paradigm of thermalization. And then maybe related to this introduction with these non-local patterns that emerge, we actually have a very peculiar and very exciting type of entanglement that forms in the system. It is exciting because it's very non-local, and it's very subtle to detect. And this is actually what interests us very much in our experiments, because we're very interested in how these entanglements may form under different conditions, and that's why many-body localization is a very exciting candidate to study entanglement in many-body systems. So you can see that these properties, they range over they cover very different fields. So they have some more condensed matter flavors, but they also have an influence in quantum information and in statistical physics. So these are very different, very broad fields in which many-body localization has attracted interest. And I think that's one of the reasons why there has been so much excitement about many-body localization over the past years, that it has really, it connects to a lot of different fields. When we talk about many-body localization, we also have to ask ourselves what is actually different to the non-interacting case. And it turns out that on a qualitative level, there are actually not so many things that are different to an Anderson localized system. So in particular, the memory of the initial state, the localization, and everything that comes with this localization is actually also present in an Anderson localized system. And it is really this non-local entanglement that makes MBL stand apart from its non-interacting counterpart. So that's also why this non-local entanglement formation is such an interesting property, because it really is the essence of the many-body properties of the system. Now, how can we study these kind of systems in our experiment? Well, we need several prerequisites to actually be able to work with that. And we in our system use neutral atoms, and there are several reasons why neutral atoms are a great candidate to do this kind of systems. The first thing is that we are working in a vacuum, and that isolates the system very well. So there is no collisions with any background gas, there's no connection to some solid state samples. There's really a perfect isolation from the environment, and that helps us a lot in maintaining the system isolated and for very long times, for these long evolution times that we need to study non-equilibrium systems. The second ingredient that we need to create entanglement in the system, and in our system we use collisions, collisional properties, and we can also have very high control over the system locally by using light potentials. And the third ingredient, in particular, in order to measure localization or to measure those entanglement properties, is local readout. And in our case, we do that with site-resolved fluorescence imaging through a high-resolution microscope. We create these systems with optical lattices. So these are counterpropagating laser beams. And when they interfere, since they're far off resonant from any atomic transitions, when they interfere, they create actually dipole potentials that are proportional to the light intensity and that have this kind of periodicity here. So with half the optical wavelength, we have a periodic potential where we can now put the atoms, and that's the potential that they see. And since these potentials are on the order, since these lattice sites the lattice constants are on the order of optical wavelengths, we can actually locally see what happens in the system by just performing high resolution imaging. And on top of that, the timescales are so slow that we can now acquire them and resolve everything on the single tunneling time level. So these are these optical lattices, what they look like. We can do them in 1, 2, and 3 dimensions. And it really allows us to study now synthetic matter in a very new way, where it's more of a quantum simulation approach. If you compare this to real solid state systems, we have now electrons that would live in this crystalline lattice in a real material. In our system, we generate this this potential that usually is generated by the ionic cores in solid state physics. For us, this is generated by laser light, and the atoms that are now moving in this optical lattice, these are reminiscents of the electrons in a real material. And with that, we can really generate a lot of different modal Hamiltonians and study them under very well-controlled conditions. And our particular experiment looks like so. So there's a cartoon depiction here. So you see this black line here, which separates vacuum. Below this black line, there's vacuum, and above it is air. And you can see down here these dots, which symbolize the atoms that we trap. And they're trapped right underneath several lenses that form a high-resolution objective. So we can see these atoms locally here. Now, by projecting several beams through this objective, we can project an optical lattice. In our case, this is a 3-dimensional optical lattice. We can then image these atoms by performing fluorescence imaging through this optical microscope. And the pictures that we then get from these kind of systems, they look like so. So you can see a lot of different dots here, and when I zoom in, you can really see that there are single lattice sites that are either occupied or that are not occupied. So there's a lot of a very high resolution readout with a very high fidelity. We can determine which lattice sites are actually occupied and which ones aren't. And what we do is we really take exactly these pictures of atoms in the vacuum chamber. We binarize them. That means we detect whether each lattice site has an atom or not. And from that, we get these matrices, which tell us exactly on which lattice sites we had an atom in this particular measurement. This is the basis of our data that we take. On top of that, now we can also project any kind of potentials. And since we have a single site resolution to image the system, we can also project with a single site resolution any kind of potentials that the atoms could see. So on top of this optical lattice, we can also now deform the actual potential landscape that the atoms see. The typical protocols for the experimental the experiments that I will present today all look somewhat similar. So we always start with a Mott insulator, and a Mott insulator is what we call where we have exactly one atom on each lattice side. So it's kind of an interaction blockade that there's only exactly one atom on each lattice side. And that's for us great because it's a perfectly unentangled state. It's the simplest state that we can think of. And on each lattice side, we have exactly one atom. And that's great for us because it's a starting point to generate almost arbitrary initial states with a very high fidelity. So what we do is we cut out now a one-dimensional system out of this initial state, which has exactly one atom on each lattice side, and we then build walls around the system of length n. And this remains then the system, and at this point tunneling is inhibited. But then what we do is we quench the system very rapidly. That means we suddenly allow tunneling and we inject disorder, and that starts a unitary evolution under the Hamiltonian for a given time t. So we start with this unentangled initial state, well-controlled initial state of exactly n atoms on n lattice side, unity filling, and then we evolve the system under the Hamiltonian. So that's a non-equilibrium evolution. So the initial state now evolves under this new Hamiltonian at very high energies. And after a given evolution time, we measure the atom number population on each lattice side. And there's one drawback of this fluorescence imaging of atoms, of single atoms, which is that we're actually only able to measure the parity of the atoms on each lattice side, which means I may actually only picture like so. So it seems like some atoms are missing, but that's actually just because on some of those lattice sides there have been two atoms. So in order to overcome this, what we do instead is that we first expand the atoms along the orthogonal direction, and then we measure the atoms in each lattice, in each column. And so the sum of the atoms in each column tells us how many atoms have been on exactly that lattice side. So that allows us now to obtain full counting statistics of the state. So essentially what this means is that this measurement here is one projection in Fock space of this many-body state. And by taking a lot of those measurements, we can characterize the state very well. The exact Hamiltonian that we are going to work with from now on is already kind of what I explained. We have tunneling term between nearest neighbors in this one-dimensional chain. We have interactions, which for us are repulsive on-site interactions. And then we have a disorder term where we really can steer the disorder potential on each individual lattice side. And in our particular case, we actually chose real random disorder, but actually a quasi-periodic potential. So it's actually not really disorder. We did this for some technical reasons. We could also have chosen a random disorder, but for results that I show, they will be qualitatively the same as if it was actually random disorder. So I'm going to use the term disorder, but it actually is technically it's a quasi-periodic potential or quasi-periodic disorder. It's not random. We are going to leave the interaction energy constant. In principle, that can be tuned, but in this case, we left it constant at about 3 times the tunneling energy. And the disorder is something that we will change a lot. So we can tune this all over from 0 to very, very strongly disordered to really explore all the different regimes of localization or localization. So I think this is all I want to talk about introducing the system and setting the stage. Are there at this point any questions to the experimental setup? I think this would be a good point to ask. Well, good. Then if not, then I will just move on with the first part of the talk. So we will, or for the remaining talk, I would like to explore these different regions of very weak disorder and very strong disorder and also intermediate disorder. Let's start with the weakly or non-disordered regime, where actually many-body localization is not expected to happen. But first, we want to establish that our system, in principle, can thermalize and is very well isolated. So what would happen in the system here? So this is this cartoon of the one-dimensional system here depicted for 8 atoms on 8 lattice sites. We start with exactly that state, which means it's a globally pure state. We always start with exactly this state, 8 atoms on 8 sites with 1 atom on each side. It is globally pure, but it's also locally pure, because if I would just take a small subset of the system, I would also always find exactly the same. For example, on one lattice side, I would always find exactly one atom. There's no mixedness in the state is not locally mixed. The situation, so that what this means is that, yeah, measuring one particular lattice side, I would always find exactly one atom, which means if I would have to associate the temperature or entropy to this, I would it would actually mean that the system locally is pure. Yeah, there's no kind of thermal distribution also involved here. Now, as we let the system evolve now unitarily under our Hamiltonian, and again, at this point, we are working in the weakly or non-disordered regime, particles can spread, they can delocalize, so the system becomes entangled. And what that means is that if I now look locally, I will not always find one particle, but instead, if I would measure the atom number, I would expect some kind of distribution which follows this kind of thermal distribution. And now I can associate the temperature with that distribution. So our system is actually locally not pure anymore, it's locally thermal, although the system remained globally pure. So we have a globally pure quantum state which locally resembles a thermal state. And now this is related to the eigenstate thermalization hypothesis that we also talked a lot about last week. Here it's not in single eigenstate, but actually a mixed state not a mixed state, a non-equilibrium state, and it's a superposition of many different eigenstates. And what we still find is that the system actually behaves very much like a thermalized system, although it's globally pure. So we, maybe a little bit more formally, we can define a subsystem, which in this case only contains one single lattice site. And under the evolution, we have particles that spread across the subsystem boundary, which bring this individual lattice site now in a superposition of many different particle numbers, for example, 0, 1, 2, 3. And that now means that if I look at the reduced density matrix, this now represents a mixed state and not a pure state anymore. So we indeed have entanglement in the system. Experimentally, we can probe this by measuring a lot of snapshots after different evolution times. And these snapshots, they all look, as I described before, they give us a string of numbers with constant sum of the total particle number that's conserved. But the individual occupations of each lattice site are going to be different with each snapshot because it's a projection in Fock space. And now what we can do is we can look at an individual lattice site and now look at the occupation of this lattice site. And you can see here, these data points here show us the experimental result averaged over many of those snapshots. And these histograms here, these bars, they show us the expectation. We can do exact numerics from exact diagonalization. And you can see very good agreement between experiment and theory. So indeed, we actually have a system that locally very much resembles a thermal distribution here. We can also quantify this now by calculating the entropy. Excuse me, is there a question? No? Okay. We have, so we can now quantify this with the entropy, the single site entropy, which in this case is even the von Neumann entropy because a single lattice site does not have any off-diagonal elements because the global atom number is conserved. That means actually compute here the local entropy of the system. And what we find over time here, so we measure these kind of histograms for very different evolution times, ranging from fractions of a tunneling time until hundreds of tunneling times, so over several orders of magnitudes here. And we find that indeed very quickly the system approaches a constant value, the single site entropy approaches a constant value, and then remains constant throughout all our evolution time. So what this tells us that we indeed reach a steady state, and the steady state does not change anymore, which tells us that the system remains isolated over very, very long times. And if we compare now this value to a numerically, so again, these data points are the experiments, you can see some small error bars behind, the solid line here, this blue line is are the exact numerics, and the dashed line is the expectation from a thermal state in the system. And you can see that this coincides very well. So that means our system indeed thermalizes and remains in that state for indefinitely. So it's really an isolated state and remains there. Yeah, with that, I would like to proceed to the second part, namely the many-valley localized regime, unless there are any questions at this point. No? Very good.
So
excuse me?
It's also clearly explained.
Also clearly explained, very good. So yeah, now we are going to explore the strongly disordered regime, where we, as I already announced, we expect now the system to localize. And what does this mean now for us? Now we apply the very same unitary evolution, but except that this time we add disorder to the system. And if particles now are localized, that means that the atom number distribution that I would measure on an individual lattice site actually would not change. I would still see a very large probability to still find exactly the one atom on this lattice site that I had there at the beginning, because the particle was not able to spread through the system. So it's still where it was before. So we can measure that. So that also means that we cannot associate this temperature with the system anymore, because there's no thermal distribution that I would find locally, and therefore I can't describe the system as a thermalized one. So we can test this in our system by performing the very same measurement as before, except this time we apply disorder to the system. We look at individual lattice sites and look at the atom number distribution. And indeed, now we find a strong peak around finding one particle. So that means we are looking at an evolution time of 100 tunneling times. So in this small system of only 8 sites, the particles would well be able to if they wanted to. But they don't. We still find a very high probability to find this single particle on this lattice site. So again, these dots here are the data points and the bars are the numeric. So we find very good agreement with theory in the system. And again, we can now look at this as a function of disorder strength. So always at this very, very long evolution times of 100 tunneling times. And we find that for very weak disorder, we find that we coincide with what we would expect from a thermal ensemble. Whereas if we go to very strong disorders, eventually we depart from this prediction. So at a disorder strength of about 5 to 6 tunneling times here, tunneling energies, we don't coincide anymore with the thermal system. So the system remains, even after very long evolution times, away from thermal equilibrium. And the interpretation of that is that particles indeed actually localized. They remain localized after these very long evolution times. So I promised you these hidden entanglement patterns. I did not mention them so far. I just talked about individually localized particles. And the reason why there is this entanglement is because there's more than just localization happening. There's also an entanglement between these localized particles that occurs. This was actually already described a long time ago, and there's this very seminal paper here where Barrison and co-workers found that for a non-interacting system, here this is again over evolution times, for a non-interacting system, the entanglement entropy actually remains constant over very long times, but as actions are introduced, there's slow growth here, logarithmic growth of the entanglement entropy that you can find here in all these different interaction strengths. And the interaction strengths just they just change the rate or the beginning of this slope, but there's always a distinct difference from the non-interacting to the interacting case. And
I have a question.
Yes, of course, yeah.
Yeah, so this is not the single site entanglement, right?
This is not.
And also this is not in Fock space.
This is not the entanglement entropy. This is the half-chain entanglement entropy, which is here. So the system was cut in the middle, and now we are talking about the entanglement entropy of half of the system size. It's not a single site.
It's not even in Fock space. It's a completely different tensor product structure, right?
It is not in Fock space. It's the entire entanglement entropy.
Yeah.
However, so far when we talked about the single lattice site, the Fock space entanglement entropy is identical with the entire entanglement entropy because a single lattice site has no other degrees of freedom and the global atom number is conserved. That means there's no other way the system could be entangled than through the atom number. This is now different for larger systems, and I will exactly talk about this on the slide and also next one.
Okay, one more question about the single site.
Yeah.
So you effectively cut off the dimension of the Hilbert space to 5 or 6. It's like that 5 is the maximum occupation number that you have.
I just didn't plot the other ones because they're essentially 0. It's extremely unlikely to find a lot of particles on one lattice site when the global atom number is conserved, right?
Right.
So in principle, we also would, I think we don't even So let me go back here. So I don't think we have like these are really, really negligible, the probabilities that we will find more than 5 particles on one lattice site. That it may occur once in a million or so, but really, really rarely.
Okay.
Yeah.
Thank you.
So yeah, what's plotted here is now the half-chain entanglement entropy. And now the question is a little bit, what does that mean actually? What kind of entanglement is that? Can we somehow get a more intuitive picture of what these entanglements, what does entanglement growth here actually means? And we asked ourselves that in particular, what does it mean for itinerant particles now instead of a spin system? So this was actually calculated for a spin system. And the way we describe this is by talking actually about 2 different kinds of entanglement. The first one is what we call the number entanglement, and that is associated to particles that would travel across the subsystem boundary. So we have now a left subsystem and a right subsystem, and these would now become entangled, for example, as particles would hop across the subsystem boundary, which now, if I would trace out the right part of the system, would bring the left one in a mixed state. So there is entanglement in the systems. It's a very simplified state here, but overall, my many-body state will look like a superposition of many different states that have different atom numbers in the left subsystem on these left 4 sides. So that's one kind of entanglement, and it turns out this is exactly the entanglement that is associated to this offset here. This first part here, this number entanglement, describes the entanglement that is so all the entanglement except for the slow logarithmic growth. So that also means that in a non-interacting system or an Anderson localized system, this is all the entanglement that the system sees. And we can see that what happens here is over one or over few tunneling times, the system generates this entanglement, and this happens by every particle becoming localized in its exponentially localized orbital. So that means it spreads a little bit, and that's the entanglement that the system has. But then afterwards, there's no dynamics anymore in the system. And that's exactly this depicted by this flat behavior here, this steady state behavior of the number entanglement. So these processes of particles tunneling across the subsystem boundary, they happen at the beginning as each particle finds its exponentially localized orbital, but afterwards there's no more dynamics in the system. Now there's a second part of the entanglement here, which is now associated with this logarithmic growth. And the question is now, what is that? How can I represent this in this itinerant particle picture? And the way we can think about this is through the configuration. So the entanglement now lies in the way particles are arranged in these 2 subsystems. So we can really think of correlations between the ways particles are in the left subsystem and the right subsystem. So if you look at this particular state here, if you just think of a very simplified state that is in a superposition of this top one particle on each lattice side, and the bottom one with this double hole pair here and the other double hole pair here, this state does not have any number entanglement if I consider the subsystem of the left half and the right half. There's no number entanglement involved, but there is configuration entanglement involved, because the way particles are arranged in the left subsystem is correlated with the way they are arranged in the right subsystem, right? Whenever I would have a double hole pair here, I have to have a double hole pair here. And that's exactly the kind of entanglement that is responsible for this very slow logarithmic growth. So what we find in MBL is that over very short time scales, particles find their exponentially localized orbitals, and over longer time scales, they stay there. But what happens is that over these large distances, there are correlations in the way these particles would be arranged. So that's really a Fock-based picture of what this entanglement would mean in a many-body localized system. And you can actually mathematically also show that in a system with globally conserved particle number, these 2 can be written as a sum. So the number entanglement can be written as one summand, and the configurational entropy is the second part, and they add up exactly in that way. Are there any questions at this point? It's a central concept, so maybe that's a good point also to ask questions if there are any.
I have a question.
Yeah.
So what's the difference between a number entanglement and a configurational entanglement? Can you explain it a bit?
I had a small. Okay, is someone speaking?
Yeah. I think you were bit, I couldn't understand everything. Could you say it maybe again, please?
Yeah, sorry. I'll wait.
Yeah.
No, you can take over. I'll wait. I have a very small question, to be honest.
Okay, so can you explain what's the number entanglement and the configurational entanglement? So
yes, yeah, very much, yeah. So number entanglement, it means that the particle number in the subsystem, or the system is in a superposition of different particle numbers in the subsystem. Configuration entanglement means the system is in a superposition of different ways these particles arrange in the subsystem. So configuration entanglement can in principle occur here, as you see in this lower depiction, can occur without having particles that cross the subsystem boundary. It really links to the ways particles arranged in these two different subsystems. Is that clear now?
Yeah, thank you.
Yeah, you're welcome. And there was another question?
Yeah, I had a question just related to that. Is that how do you treat the cases where you have like, boundary crossings, at the same time you have configurational changes? Like,
So in the end, of course, both happen at the same time, right? And that's exactly what you mean. But you can, in each sector, in each particle sector, you can now look at all these configurations. I'm going to actually explain a little bit more on the next slide how we measure this in our experiment. So maybe then everything becomes clear. Maybe remind me again after the next 1 or 2 slides if still I'm...
Sure, I'll do that.
Thanks. Good. Yeah, so this is how we look at these two different entanglements, like one that actually where particles actually it's more related to particle spreading, and the other one is more related to correlations between particle arrangements. And maybe one remark to this, the lower one, I mean, we can see it already from this depiction here, from this numerics. The lower one, the configuration entanglement, is the one that requires interactions, because here we have different particles behaving in a correlated way. Whereas the number entanglement, we don't really need correlations between different particles. It's really just related to particle spreading. And that also explains why, without interactions in the Anderson localized system, and these blue data points here, we don't have any configuration entropy, but we have the same amount of number entanglement as we would have with interaction. Yeah, so it's really the configuration entanglement is really an interaction effect, whereas number entanglement is not necessarily. Yeah, so now let's look at these two different entanglements separately. So how do we measure this in our experiment? Well, the first one is the number entanglement, and as I mentioned, that actually is related to the transport in the system. So we now look at the left half of the system. So that's our subsystem that we consider, and we compute the number entropy, and this number entropy actually can compute like P n log P. So we look at we count the particle number in the subsystem and compute the associated entropy. What we find is that indeed that grows over the few tunneling times, but afterwards here you can see from 10 to 100 tunneling times there's no significant growth anymore. So particles first find their exponential orbitals over a few tunneling times, but then they remain where they are over very, very long time scales. Here I didn't plot the thermal expectation value because that's very far away. That's actually about at the top of the slide. That's where the thermal expectation value would be. So we are really not in a thermal system here. We find a steady state of the number entropy that's very far away from what you would expect for delocalized particles. We are here in a strongly disordered regime. So that's about the very right end of this graph that I showed, about 9 times the tunneling energy. Now the more subtle part of the entanglement, that's now related to the configurations in the system. So the way we measure these is now by looking at each of those snapshots separately. So I will call the configuration in the left subsystem A and in the right subsystem B. And now what we do is we look at the correlations between these two different configurations. So the probability that A and B occur together minus their individual probabilities tells me how much these two are now correlated. Do they have the tendency to occur together, or do they have the tendency to just never occur together? Like, do they exclude each other? So these are all the correlations that we measure here. And we sum now over all different ways that particles could possibly arrange in these two subsystems. And this gives us now the correlations between configurations in A and B. And it turns out that this is actually proportional to the entanglement entropy. So it's a probe for entanglement in the system. Now, maybe one remark, we are measuring here in one particular basis, right? We are projecting always in the same basis. Therefore, in general, there should be entanglement also in other orthogonal to this basis where we are not measuring. However, in this case, that's actually okay, because our picture for this is that due to the disorder, the entanglement is somewhat similarly spaced in the different directions of the different bases, and therefore we're actually probing the entanglement in the system. So that's it's related to the fact that as we always do project the system, we actually measure entanglement, although we are not measuring along orthogonal bases. So we can actually numerically verify this for all kind of different parameter regimes that we are considering, and we always find a perfect proportionality between this correlator here, which we constructed, with the entanglement entropy. So that's a new tool of how you can measure entanglement in a many-body system, and in particular, it's very suitable for many-body localization. It's really an observable that's constructed around finding the logarithmic growth of entanglement in a many-body localized system. And so we can now do this experiment. So again, over evolution times of several orders of magnitude, we are now measuring these configurational correlations, and we find that they grow logarithmically in time. So there's a slow growth here that we find of these correlations. And now the sum of the number entropy from the previous slide together with this configurational correlations gives us now the entire von Neumann entropy of the system. So there's this initial rise, and then there's a slow growth of the configurational correlations, just like we saw in the numerics from Jens Bardersen papers.
Could you comment how big is the system at this point, and how many measurements do you have to make to evaluate that?
Yeah. So that's a good point. So here we are working with up to 8 particles on 8 sites. In general, now, if I want to map out all the probabilities how particles could possibly arrange in these 2 subsystems, for very large systems that may become very challenging. However, I think that's a general property. If you want to measure entanglement entropy in a system, there's just a lot of matrix elements that you have to know and measure. So that's a problem in all systems where we want to measure entanglement entropy. And this correlator the good thing about this correlator is that it actually we only need to measure those components that are actually populated. So in other ways, there may be a lot of configurations that are never populated whatsoever. For example, 8 particles on one lattice site. We automatically see that this doesn't occur. So I think if you compare now the number of snapshots that you need to get a certain error bar on this correlator compared to other ways of measuring entanglement entropy, this is actually rather efficient, in particular for many-body localization. So what we used here was several hundred snapshots, about 500 to 600 snapshots per disorder, and this is always averaged over several disorders, right? So these are several thousand measurements, which is actually for us decent. I mean, for some other observables, one would need tens of thousands of snapshots, and for some superconducting circuits, they use even more than that, right, as measurements. So that's about the measurement effort that it takes to measure this logarithmic growth here.
Thanks.
Yeah, this is also maybe answer your previous question, Abhijit, right?
Yeah, partly. So I understood how you're doing configurational. What I could not understand is like how you exactly doing number entanglement calculation.
Mm-hmm. So the number entanglement is the way we compute this is exactly Pn log Pn. So very, very simple.
Okay.
And the reason why this works is that essentially you have different your density matrix essentially has different blocks, and the number entropy doesn't care of what is in this block, it just cares of the overall probability for these blocks. And then the configurational entropy now acts within each of these blocks.
Right.
So that's kind of the mathematical separation of these two. So the number entropy really considers only the probability to have a certain particle number in that subsystem. And the configuration entropy now looks at within the sector of having a certain particle number in that subsystem, how are they arranged, and that now gives you the remaining part of the entanglement. And now there can of course also be entanglement in the phase degree of freedom, and that's exactly the other axis along which we don't measure. But disorder and many-body localization, that doesn't matter much, and it's actually always still proportional.
Okay, fair. Thanks. That explains everything.
Very good. Thank you very much. Yeah, and I think that's also everything I wanted to talk about with in a strongly disordered regime. So now, as a last part of this presentation, I want to also cover the intermediate regime, the quantum critical regime. And I personally find this the most exciting one because it is really the one where we have the hardest time to understand what happens in the system, and both theoretically and experimentally. Usually when we think of quantum phase transitions, we think of ground state quantum phase transitions. And here I've shown pictures of the favorite quantum phase transitions in cold atoms lattice systems, where from a superfluid where we have high coherence in the phase degree to a Mott insulator where we have no coherence in the phase degree of freedom. And what we think of usually in these kind of systems is we tune some control parameter, for example, the interaction strength, and at a critical point we find diverging correlations, we find slowdown of dynamics, so a lot of dramatic things that happen, but very well understood in the framework of Landau phase transitions and everything that goes together with it. Now we are dealing with non-equilibrium phase transitions. And that complicates things so much because we now have to consider all the different eigenstates that are far away from the ground state. And you can here, just as a small picture here, this is now the localization of each individual eigenstate, and we can really see as a function of disorder strength. Red means localized, blue means delocalized. There's some, well, I would say it looks simpler for strong disorder and for weak disorder, but here in the middle, it's really very difficult to find some way of understanding this. And what I want to say with this picture is that looking at non-equilibrium phase transitions really requires completely new concepts to look into, and therefore we are now really at the beginning of understanding what is the right way to think about that. What we did in our system was we tried first some more macroscopic observables, in this case associating the particle arrangement in the system now with the transport properties of the system. And we can do this through the two-point correlations. So the two-point correlations, density correlations in the system, they are related to transport in the system, because every time a particle hops from one lattice side to another one, we find a double on-hole pair that creates correlations, and therefore movement of particles is associated to density correlations. So we now can look at the average distance particles hop in the system, and that's for us the transport distance of the system. So particles, how far particles would move. And now we do this now for different disorder strengths across the critical regime. And in the weakly disordered regime, the thermal regime, we find very quickly that we reach the system size, so particles actually spread throughout the entire system. If now we look at this as a function of distance, so consider one side, and when we look now at all the other sides, how strongly are they correlated with that initial side, we find a very flat distribution. So particles indeed now spread completely throughout the system. There's no structure whatsoever. Particles are just completely delocalized. In the strongly disordered regime, we find something very different. So within few tunneling times, the transport distance reaches its steady state of around one lattice side and then remains there forever, indefinitely. And also as a function of distance, from our reference side, we can now see that only nearest neighbors are correlated and all the other sides are completely uncorrelated, which means particles are somewhat able to go to the nearest neighbor, but that's where they get stuck. So that's just another very direct proof that particles are localized in the system. Yes, there's a question?
Yes. So it's not really forever, right? It's logarithmically slow.
Yes.
Eventually it will delocalize.
Well,
in exponential time, in the tunneling time, it would delocalize.
Okay, there's in principle, no. In principle, MBL remains indefinitely localized. I know there's been some recent developments in the MBL community that questions that statement. Right now, I'm still, well, I think, yeah, it's not. I think it's not 100% settled right now. I think in this picture of this work here, people were still thinking that it remains indefinitely localized. That's my understanding.
Okay.
Yeah, but there's still a lot of movement in the MBL community, also from the theoretical side, how strictly localized particles actually remain. there's, for example, some work that now suggests the double logarithmic growth of the number entanglement actually. So I think it's not 100% settled. I think from an experimental point of view, we still tend to say, okay, it's localized, so particles actually remain.
Look, if you say that there is a logarithmic growth of entanglement,
yeah,
it means that there is a logarithmic growth of the correlation functions per what you were saying, which means that at some point they're correlated at all distances, and which is delocalized, right?
Well, the entanglement does not necessarily need to, so logarithmic growth of entanglement does not necessarily mean logarithmic growth of the particle delocalization, because as we've seen here, we can have growth of this configuration entanglement, but the number entanglement, so the actual spreading of particles, remains constant, right? So the fact that there is this logarithmic growth of entanglement does not mean that there is a logarithmic spreading of particles.
Mm-hmm.
And that's a very important distinction here. So particles, within the scope of this talk, particles are actually really stuck. They remain localized indefinitely. And
yeah,
now
well, it depends on whether you really increase overall the possible configurations, because that entails also the number of. But yeah, I understand this is delicate.
There's a certain level of complexity at which we, as an experimentalist now here, can see things, and I think that's where we would say, okay, they are stuck. But I realize this is not 100% true, and in particular, over the last year or two, people have looked more carefully into how stuck are these particles actually, and found that there is still some delocalization actually happening. So many delocalization technically is actually not a perfect insulator and is not perfectly thermalized. That's the new developments, but there's still some open questions there.
Yeah. Thank you.
Yeah, you're welcome. So yeah, and then so what you find here is that here again, after very long evolution times, we find nearest neighbor correlations, but no correlations across the system for all the other lattice sites. So particles actually are localized here, as far as we can tell. And then what's interesting is in the intermediate regime in the critical regime at intermediate disorder, there is some slower growth. So particles don't grow immediately to a system size. They're not stuck. There's some slow growth, and only after 100 tunneling times we reach the system size, which in this case actually is 12 sites. And also we find now correlations that extend throughout the system, and some sites are more correlated than others. So we really can see that there's some parts of the system where we have particle exchange, right? Remember, any kind of correlations here mean that we have particles hopping between these sites. But there's other sites that are not correlated whatsoever. For example, here, the third site here, there's no correlations, but at a distance of 9 sites, we find correlations. So there's a complex network in the system that allows transport, and that does not necessarily include all sites. And we can now quantify this transport properties here by looking at the slope of how quickly does this transport distance approach the system size, and it actually decreases. So this exponent decreases as we increase the disorder strength. So there's really a subdiffusion happening in the system that subdiffusion would be anything below 0.5. So you can see here this subdiffusion gets weaker and weaker and weaker until eventually, for very strong disorder, we approach 0. So we essentially don't have any transport anymore in the system. And now, when we saw that we actually have slowing down transport, but also happening in this complex network here, we asked ourselves, what does it mean, this complex network? How complex is it? Is it on the level of 2-point correlations, or is there something more complex happening in the system? And to quantify that in our system, we looked at higher order correlations, multi-point correlations. So the connected correlation functions at order n, so where we would always subtract all the lower order contributions and really only look at correlations at degree n in the system. And when we compute this in our system, we can't measure all. So it would take a lot of statistics to measure high order correlations on order 4, 5, or 6. But what we can do very well is to quantify the average strength of correlations. And that's exactly what you see here. So the average strength of the correlations at order n now for different disorder. So let me walk you through this plot. It's a little bit, there's a lot of information in this plot. So let's start at weak disorder. in the thermal regime, and as you can see here, so the bars are theory, and the data points are these round circles. And a small correlation order, so 2, 3, 4, 5. You can see how it decreases with the order of the correlation that we are considering. So the higher the order at which we are looking for correlations, the weaker are the correlations in the system. And that's exactly what you expect for a thermal system. You actually expect that the system is uncorrelated, in particular at the higher order level. As we now look at the opposite end of the disorder axis here, at very strongly disordered system, we find again that as we increase the correlation order, the average strength of those correlations decrease. And that's also telling us that many-body localization actually is a weakly correlated system, because, or in that sense, weakly correlated, because we only find 2-point correlations between the nearest neighbor, but 3, 4, 5 order, fifth order, there are not many correlations in the system anymore. And the reason for that is really that these configurational correlations, they are there, and they are of course multi-point correlations, but they're actually weak compared to what could be in the system. So these are very, very weak correlations that are present in the system. And when we go now into to the intermediate regime, we find very strong correlations. And even at very high orders, we find the system is highly correlated. So there's a very complex entanglement structure in the system. We can take 5 or 6 sites in the system and find very strong correlations between them that cannot be explained by 2 or 3 or 4-point correlations, but only at these high orders of 5th, 6th, or 7th order or so. So a very highly correlated system with a lot of entanglement, and that really explains why it is so difficult to numerically capture what's going on in the critical regime. So maybe to give you an overview of the different kinds of entanglement that we find in the system, in the weakly disordered regime, we find that all lattices are correlated with all other lattices. There's a perfectly delocalized system, which again looks locally thermal, but really a very, very homogeneous entanglement. And then for the many-body localized system, we find strong nearest neighbor correlations, and then this weak logarithmic growth of entanglement that spreads throughout the system, which is depicted here by this shade, blue shade. And then in the critical regime, there's a very complex structure of the entanglement. So this really shows us that these correlations are, they're very difficult to capture, and there's different subgroups that are correlated at some order. So it's very, very difficult and very difficult quantum state to describe. The entanglement structure here is very complex. Yeah, with that, I would like to thank the team that I was working with together over the past years. And it was really a pleasure to work with all these different grad students, and of course, Markus Greiner, so Perrin, Joyce, and Sushin, and also our former grad students, Matthew Rispoli and Alex Lukin, that have left recently, and Robert Chitko. So it was a great pleasure. Thank you very much all for your attention. Thank you.
Well, thank you so much, Julian, for a wonderful talk. We had quite a few questions. Are there some more questions for Julian?
Yes, I have one question. You confine yourself to nice, what should I say, neutral atoms.
Yeah.
Would someday you'd be interested in doing these experiments with the fermions and bosons, so to say?
So here we're using bosons. I think you're right. I don't think I mentioned that. It was implicit. Many particles on the other side, but I may have forgotten to mention that. Yeah, thanks a lot. So these are actually bosons. One could also do these experiments with fermions. So many-body localization would also be possible with to observe with fermions, and has actually been observed in other experiments with fermions. In our case, we have bosonic atoms in this experiment, and it's not so easy for us to switch to fermions. So we are probably going to go on with bosons. But qualitatively, I am not aware of any qualitative differences between bosonic and fermionic many-body localization. So I don't expect any new physics actually that we could observe with that.
Okay, just one more question. How do you really define a critical system here?
Mm-hmm. That's a good question, and I think that's also not really settled, not even from the theoretical side. So it is it is not even clear. So yeah, that question is that has a lot of layers, which I could reply here. Maybe one remark is that we are not looking at, like usually we would say we are looking at one eigenstate, the ground state, and we look at its properties now. And here it's not only a spatial thing, but also a dynamical thing, right? It's because we are looking at critical properties not only spatially, for example, a correlation length, but we are also looking at an evolution time of the system. So it's a new kind of criticality that is not really, it's not really clear how to define it. And I mentioned earlier, I think that talking about these non-equilibrium phase transitions requires new theoretical and experimental concepts to actually even really describe that. What we know for many-body localization, or for the transition from thermal to many-body localization, is that the transport properties change. We know that the entanglement properties change. So we know there is a transition. And we also know that there is criticality in the sense that we can actually define critical exponents, for example, in terms of how the localization length diverges or increases as we go from many-body localization to critical. However, as I mentioned, it's really hard to capture this numerically, and there has been various approaches, for example, with RG methods, to somehow capture that, because we really can't do numerics for larger system sizes than 20-something spins. And so there's a lot of open questions also from the theoretical side and in this particular regime. And it would be really exciting to study slightly larger systems and actually answer some of these theoretical questions experimentally. For example, what these critical exponents can be measured from finite size scaling with a few spin chains, as I mentioned, for up to 20-something spins. But if now we can go to slightly larger systems, maybe we can actually provide answers that are currently not accessible with numerical methods. So that's maybe gives you some ideas of what criticality may mean here, but there's a lot of things about that are not understood. Yeah. I think you're muted.
Are you not worried that with finite system you may miss out things like Bose-Einstein condensation kind of properties?
In this system, we are really working very far away from the ground state. So if we would go to and we are also having strong interactions. Now, if we would go to the ground state and reduce the interaction strength, we would indeed expect something like Bose glasses, not quite like a Bose-Einstein condensate or superfluid in the presence of disorder. But here we are very far away from the ground state. So we really can think of injecting a lot of energy into the system here. So I think any kind of properties that would be related to Bose-Einstein condensates are completely lost in the system.
Can you envision any steps in higher dimensions?
So 2 dimensions is definitely possible, and also something that we would be interested in doing here. What is one of the challenges in 2 dimensions is that this full counting procedure that we do to actually detect whether we have 0, 2, or 4 particles on one lattice site is a bit more challenging. We can actually do that. We have done that before by having multi-layer readouts, so essentially moving atoms into different layers. If there are 2 particles on one lattice site, then we split them and move them to the next layer, and then we read out layer by layer and then count the layers. So that is possible, and it may be something that we could pursue in the future, but we haven't done that so far. In 2 dimensions, of course, there's also many open questions in many-body localization and also other associated phenomena. So that would also be really exciting to look into. Yeah. Mm-hmm.
I agree. Any other questions for Julian?
I had one regarding your remark that when you mentioned that fermionic systems and bosonic systems may not have that much of a difference. In context of configurational entanglement, like the way you presented it, I was wondering, wouldn't fermions have a different type of configuration that is allowed? Because now you cannot have like single site occupations, and swapping fermions is not going to give you anything. So wouldn't there be some difference in configurational entanglement?
You would. So on a quantitative scale, yes, there are different kinds of configurations that you have to account for. But qualitatively, you would have the same logarithmic growth of the configuration entanglement, and so there's no qualitative differences. There's different ways of exactly computing that and measuring that, but on a qualitative level, I don't expect any differences here.
Okay, fair. Right. Oh, I understand the basis behind your remark. And another thing that I wanted to understand was like, what have you exactly plotted in the last thing where you're basically showing expansions of different correlation, different order correlations?
So what we computed each time is average strength of correlations, and so measuring 6-point correlations is just extremely challenging, right? Because if I have exactly 6 points, and I mean, each order is just much more difficult in terms of statistics to measure that. But at the same time, the number of groups of 6 sites in the system also grows combinatorially, right? So there I also have a lot of different groups of 6 sites. So if I now say I'm not interested in the strength of these particular 6 sites, but I'm interested in the strength of the typical strength of 6 sites in the system. That is actually something that's experimentally accessible. And that's exactly what's plotted here. Okay. How strongly are typically, or on average, 6 sites correlated, or any number of sites, the order here, name the order that you're interested in the system. And that is also some information that's very interesting to know, because it tells you how strongly correlated is that system at that order, right? And it's experimentally much more accessible because there's just a lot of different groups of 6 sites in the system.
True. I mean, combinatorially, you'll grow really fast as you increase the order.
Yes, that's also why we can't compute higher than 8th order here.
Fair. Thanks.
So, and eventually, it's not anymore a data taking problem, but the data analysis problem here after order 8.
Right. Thanks again. Great talk.
Thank you. You're welcome. I see something in the chat.
Yeah, Christoph, do you want to voice your question?
Yes, can you hear me? Hello?
Yes, we can.
Hello. Yes, so for some time I was using the relaxation method for solving the equations of motion, like in Ginzburg-Landau theory. And I have just a question, because if we get the solutions, we minimize the free energy functional. And the question is, would it be possible that if we are out of equilibrium, the system is not fully thermalized, can we use similar methods to predict the positions of atoms and to relate to your experiment?
I'm not sure if I understood everything acoustically, but I think I hope I got the essence. So the one important remark is that we are really very far away from the ground set, but yet we are not thermalized in this many-body localized system, right? So that means we looking at free energies or looking at Landau theory in the system, I believe would fail and would not give you any useful answers. Now for the position of the atoms, we're actually starting with a homogeneous density, and we're applying disorder, well, different kind of disorder, but also once we average over the disorder over the different disorder patterns, we don't expect any differences in density. We expect still a homogeneous density, right? Because we started with homogeneous density, so after evolving the system, we still expect a homogeneous density. Now, for a particular disorder pattern, it may be slightly different, but after averaging over disorders, that should still give us a homogeneous density. I'm not sure if that's exactly your question. Please correct me if I'm wrong here. I can't hear you.
Oh, that is perfect.
Yeah, that's good. Okay, good, great.
Any other questions?
Yeah, one last question, if I want, maybe. When you go from 1 dimension to 2 dimensions, there's a difference between what kind of phase transitions are allowed. And in my mind, phase transitions are very good representation of what you call correlations. So would you expect something very, very new, qualitatively also, not only computationally different in 2 dimensions?
Maybe again, one remark. I suspect what you have in mind are equilibrium phase transitions of what is allowed in 1 dimension and the other one. In non-equilibrium, it's really it's really very, very difficult to actually know what is allowed or what is not allowed. Now for MBL, it's also not really settled to what extent 2D MBL actually exists or does not exist, or what kind of features, what kind of localization, or what kind of suppression of transport do we expect in 2D far away from equilibrium, and what don't we expect? So I think that's not really clear, but it's true that correlations are still going to play a major role. And also people look at these configuration correlations, also just at entanglement entropy in 2D systems as well, try to understand what kind of features of MBL are also present in two-dimensional systems. But as numerics, there is much more challenging than in 1D. We have even fewer answers there than we have in one-dimensional systems. Yeah.
Okay, so I would say let's thank Julian one more time for a great presentation and for patiently answering many questions with great clarity. I'd also like to answer all of our, I'd like to thank all of our presenters, quite a few of which are in the audience. Also, I'd like to thank my co-organizer, Alyosha Hammer, and in fact, all our participants. I think we've enjoyed a very lively audience these past few weeks, which is great. And so stay safe and hopefully see you in the real world sometime.
Thank you for the great meeting.
Thank you very much. Yeah.
Thank you. Bye.
Bye.